Good morning everyone, and today we will discussing internal flow, especially entrance flow and developed flow. These are important concepts in fluid mechanics.
That's right! Entrance flow occurs when fluid enters a pipe or conduit from a larger reservoir. It typically shorts with an unsteady flow and gradually transitions into a steady flow called developed flow.
In addition, we have fully developed turbulent flow in a circular pipe. We will consider fully developed turbulent flow in a circular pipe as a classical internal flow. Example, a laminar flow become unstable at around Ra is equal to 2000 and the transition of a fully turbulent at Ra 4000. So under the foul developed condition, viscosity affect the flow across the interpipe. And we have argued that the velocity should in a principle have a universal law of distribution. So in a linear sublayer, we have u over v squared is equal to yv over v, and for the log layer, we have u over v is equal to 1 over k Kelvin n over yv squared over v plus b. And so we have the near center line region formula also. So this formula in a fully developed turbulent flow in a circular pipe, assuming the log part of a layer is prevalent across the most of the pipe, we can evaluate the average pipe velocity. In the screen, we will saw a formula. For the friction or the pipe friction factor, we have also this formula. This shows that the integrated expression for V is a skin fraction relation, which can be written in terms of Darcy friction factor. F is equal to Fc.
Could you explain why this transition from entrance flow to the belt flow is important?
Of course. Entrance flow usually has fluctuations and turbulence due to the pressure differences and changes in velocity. However, as the fluid moves further into the pipe, these fluctuations decrease and eventually it reaches a steady state with consistent velocity and flow conditions. So this is the developed flow.
So, how do we study the linear flow in a pipe in a lab?
To study a laminar flow in a pipe, we will set a transparent experimental apparatus. We'll use a transparent pipe with flow rate control, some manometers to measure pressures differences, and a dye to visualize the flow.
That sounds interesting. Could you walk us through the experimental procedures?
Sure! First, we'll connect the pipe to a steady water supply. We'll adjust the flow rate using the control valve to ensure a laminar flow condition. Then we'll introduce some dye into the water to make the flow visible.
Additionally, we'll place the manometers at various points along the pipe to measure the pressure differences at the location.
Once everything is set up, we can observe the laminar flow patterns in the pipe. We'll be able to see the smooth, even flow of the dye, showing that the fluid is moving in distinct layers without mixing.
That's fascinating. By measuring the pressure difference, we can also gather data and calculate parameters such as flow rate and head loss.
Furthermore, the velocity profile in a fully developed laminar flow in a pipe of a diameter d is given by u is equal u o close open parenthesis 1 minus 4r 2 over d2, where r is the radial distance from the center, and this is the formula that we will use. And now, let's move on to the studying laminar flow between parallel planes. This is also known as planar flows.
How does planar flow differ from flow in a pipe?
So what I have observed in laminar flow between parallel planes, the fluid moves between two flat surfaces instead of through a pipe. So we can visualize this by setting up an experimental setup with two parallel planes similar to a mini channel.
We can now control the flow rate at these separation distance between the plates. By adjusting these parameters, we can observe different flow patterns and measure various properties.
Just like in the pipe experiment, we'll introduce a dye to visualize the flow and use pressure sensors to measure pressure differences between the two plates.
In addition, for the laminar flow through circular pipe, we have the formula for shear stress. We have stress is equal for the negative R over 2, close open parenthesis, the P over X.
So, this will help us understand how the fluid behaves in confined spaces and determine factors like velocity, profile, and drag forces.
Exactly. By conducting these experiments, we can analyze and comprehensively By conducting these experiments, we can analyze and understand internal flows more comprehensively, enabling us to improve design for various engineering application. I will see you again for our next discussion. Bye-bye!